Okay, we're going. Okay, so last time we were talking about scalar line integrals, right? Remember the big idea of a scalar line integral is it's really just like a double integral, just like a triple integral, just like a single variable integral. You got a problem of some sort, you chop it up into little pieces. And then you add up the answers that are easier to compute on those individual little pieces. So chop it up, add it up, just done over a different kind of a domain, that being now a curve in space. The distinguishing feature is that the domain itself is of a different dimension than the world that it lives in. So here's a curve in 2 dimensions, or 3 dimensions of the same picture, morally, right? So this is how you do chop it up, add it up. On such things. We got this notation to represent this construction, and this is the name for it. How to compute it? Well, we're going to kind of rip off an old idea, namely the idea of change of variables. Big idea there is if you can view the domain that you don't like as being the image, right? If you can view it as being an image of a domain that you do like, right? Such as an interval in this case on the t-axis, right? This is fantastic. This is a single variable calculus, right? This undesirable, weird, dimensionally awkward domain is the image of this much nicer domain. So it's the image by way of a parameterization, and there are some different details, but effectively, morally, what we're going to do is pull back through this function, aka pull back through the parameterization, which mostly, as you recall, amounts to plugging in. The one little sticky business is this length ds. You got to get your hands on how do you quantify size on a piece of curve, and of course its length, and that's easy to relate to size in our pullback domain, namely dt, because distance equals rate times time, and we already know how to compute rate. So that was kind of a freebie. Got lucky. Okay, so that said, we have for a scalar line integral, here's our formula. Let's do one. Okay, so I'm going to do 4 examples, all at the same time, because they have so much in common. And I think it's interesting to do them together to emphasize how much they have in common. But first of all, let's talk about the setup. Suppose we have an irregular wire. So, the wire has more mass per unit length in some places and less in other places for whatever weird reason. Right? Okay. It is following a curve described by this right here, which you'll recognize as a parameterization. So conveniently, the parameterization we're going to need is given in this case. That's a lucky break. It won't always be that convenient. Sometimes you have to create your own parameterization. We'll see some examples of that. The irregularity is represented by the fact that the mass per unit length is, again, not constant, and it's given by this expression right here. Okay, so the 4 examples I'm going to do are I'm going to compute this thing's mass, I'm going to compute both coordinates of its center of mass, and I'm going to compute its moment of inertia around the x-axis. So that's 4 separate examples. But they all have a lot in common. So anyway, I'm getting ahead of myself. All right. First of all, let's talk about the Riemann sums. I'll come back up to that parameterization stuff in a minute. First of all, the chop it up, add it up aspects. Mass is an accumulating quantity. Sum of a bunch of little pieces of mass that you would get if you were to chop that wire up. We have an existing formula for the x-coordinate of the center of mass. We have an existing formula for the y-coordinate of the center of mass. And we have an existing formula for moment of inertia. So write those down. I've kind of got integrals. Maybe notationally we might gripe and say we need a ds. So fine, dm, in all of these examples, dm is mass per unit length times length. Right? And now we have, in all 4 of these examples, scalar line integrals. Right? Why don't I just do this? Now I can see better. There we go. Okay, so 4 scalar line integrals. Everybody on board? Okay. All right. here's the thing. These 4 scalar line integrals, they're all scalar line integrals over the same curve. Let me just clean up the mess. All over the same curve. They're all on the same wire, same curve, same parameterization, same range of values of t, and the mass per unit length also same for all of these, right? So these are the common features that we're going to be able to share in all these examples. So for example, for this first scalar line integral, when I get around to trying to figure out how to rewrite ds, and I've got to compute my speed in order to do that, so we take the derivative of the parameterization to get velocity. We compute the magnitude to get the speed. And that stretching factor, right, this stretching factor, rewrites ds in terms of dt. There's that stretching factor. And it does the exact same in all the other examples, because they're all over the same curve, same parameterization, same velocity, blah, blah, blah. Right? So same stretching factor, which is computed with the same formula, square root of 1 plus 4t squared. Notice also, because I'm using the same parameterization, my formulas for x and y are the same. So x is t for all these examples, because it's the same parameterization. And y is t squared for all of these examples, because again, same parameterization for all of them. So you'll notice, for example, okay, here's a y t squared. There's a y t squared. All these examples, same deal, y t squared. Be careful with this one here. We have y squared. So that t squared, that is y, that t squared gets squared. It's easy to oops and accidentally forget one of these squares right here. So slowly and carefully. Okay. All right. So it's the same kind of plugging in process for all these examples. And then, of course, now we do get down to different integrals to be computed. Sure, fine. So that's the integral you're eventually going to have to compute to get the moment of inertia. Different integral to get the y-coordinate of the centroid. Fair. And likewise, different for the mass and different for the x-coordinate of the centroid. But still, 4 basically parallel examples. What do you think? Everybody okay with that? Okay. All right. Here's a different example. So let's suppose that we have a plot of land. There's the plot of land, right? And I'm going to put a fence around this plot of land, and the fence is going to follow the perimeter. The plot of land being a disk, the fence is going to be a circle, and we're just going to call it a unit circle just to keep it convenient. Okay. So we're going to put a fence on that purple circular path. Okay, here's the thing that's going to make it weird. The height of the fence is not going to be constant. And now why might this be? Maybe I've got a garden on one side and I want the fence to be lower to give it more sun. Maybe I've got a house or a sitting area on another side. I want the fence to be higher for privacy or shade or what have you. So different height in different places. And so if I want to know what the area of the fence is, I can't just multiply height times length of the fence, the circumference of the circle, because the height's not constant. Right? Okay, what I can do, however, is argue that for a certain piece of the fence, now here's my piece of fence, sort of, blowing it up large. If I focus my attention now on just a little bitty piece of fence of length ds, I've got a formula, H, that tells me how tall the fence needs to be there, and height times width gives me area. That makes sense to everybody? Right, so I'm doing a chop it up, add it up along a curve. The thing that I'm adding up here happens to be pieces of area, and circumstance, I know the height, and height times ds gives me my dA, and lo and behold, scalar line integral. Is everybody comfortable with that? I mean, okay, yeah, cool. And so again, it comes down to now kind of plug and chug. Now we do have to deal with the parameterization. Note in this case, the parameterization not given. Like in the last example. Here we're going to have to make up a parameterization. That said, fairly convenient. Again, the path that we're parameterizing is the unit circle, and we have a pre-existing, old memory from chapter 1, how to parameterize the unit circle. There you go, cosine and sine, no problem. Does everybody remember that? By the way, in case it's not already obvious, going to need to be able to parameterize curves, right? And in order to parameterize curves, you have to remember the parameterization methods, and we talked about several of them back in chapter 1. So this would be a good time to go back to chapter 1 and review and make sure that you remember all those various little tips and tricks on how to parameterize curves. Okay. All right. This one we happen to recall. Okay, so as usual, we take the derivative to get the velocity. We take the magnitude to get the speed, and that speed is our stretching factor. And so on a little piece of curve here, I can rewrite ds as speed times dt, and that speed is 1. Everybody all right? It's all plugging in from here. The height, bad color choice. The height is given as that formula. What is x? Easy to lose track of what x is. Where does x come from? Don't forget x is part of the parameterization. Right? It is specifically the first coordinate of the parameterization. The parameterization tells all, right? When you're doing the pullback. And so x is cosine t, like so. And now you've literally got a single variable integral, and you plug and chug. Okay, what do you think? Yes. Yeah. Oh, yeah, thank you. Right, so this, I do need to go all the way around the unit circle, and this makes the unit circle specifically where t here is kind of the angle that is a measurement of how far I've gone around, right? And in order to trace out the whole unit circle, I need that angle t to go 0 to 2 pi. And so that means that t goes from 0 to 2 pi, because, again, that's the t bounds. Is that all right? Okay. Good deal. All right. Yeah. Okay. All right. Here's another example, kind of. Actually, I'm going to go into this kind of as if this is going to be like the other examples, but actually something qualitatively different is going to happen here. Something a little bit weird is going to happen. But let's approach this, as if scalar line integral is going to work out. Let's compute work. Right? So specifically, suppose I have a curve through space, and let's suppose I'm going to move along this curve. And as I move along this curve, I'll be applying forces, and the forces I'll be applying are indicated by these arrows. So, for example, when I get to this point right there, as I move along the curve, I'm applying a force like so, off of the direction that I'm going. But anyway, that's the circumstance. How do I compute work? We wish we could say work is equal to force dot displacement. But this formula makes certain assumptions. This assumes that your force is constant, which you can see here it isn't. Force is not constant, right? The force varies. The force depends on where you are. Different forces in different places. This also assumes that your displacement is over a straight line path, which this isn't. Right, so this formula doesn't work. You cannot just say work equals force dot displacement. It does not account for the curvature of the path. It doesn't account for the non-constant nature of the forces. So we're dead in the water on that. Okay. So as we do, this being a calculus class, right? Chop it up, add it up is what we're going to do. I'm going to chop this up into little pieces, itty bitty little pieces like this, for example. And on such pieces, notice that little piece of curve, it's close, but not quite, to straight. It is close, but not quite, to say that the forces are constant. Again, not exactly constant, right? But it's such a small little piece of curve, there's just not much distance over which the force has a chance to really change very much. Right? So we have approximately straight pieces of curve over which we're applying approximately constant forces. And so on these little pieces, I can say force dot displacement. And then we'll just add up over the entire curve. Details to follow. More details to be written down. Does that make sense to everybody? All right. Okay, now there's a detail that I swept under the rug that we got to come back and talk about now, and that is this business about orientation. This has to do with one of the features of work. Work is different from a mass application or something like that, in that it matters which direction you go, right? So if you walk up a mountain path, that's a positive amount of work that you exert, right? If you walk down the mountain path, it's as little work as you want it to be. It's technically negative work, right? You could put on a pair of roller skates and daredevil on down. You're not really doing any work at all. And you're creating kinetic energy. So it's literally negative work. So the direction you're going matters. That makes work a fundamentally different kind of a quantity than mass or area or something like that. So in order to be unambiguous, I can't just say, well, I'm going to move along that curve. The curve, like imagine this were a road. If I just say, I'm going to drive that road, well, which way are you going? Could be either. It's not clear. Right? So a curve just kind of sits there, but we need to talk about an oriented curve. We need to say specifically, I'm going this way. Along the curve. That choice, and you only have two choices, right? You can go that way or this way. Of those two, that choice is called the orientation on that oriented curve. Is that all right? Okay. So when you're computing work, it's not sufficient to say I want to compute the work to move along a curve. You have to say work moving along an oriented curve. All right. Now that said, let's get to the details. For this little piece of curve right there, let's talk about how much work does it take to move along that little piece of curve. Well, I have my position differential, dx, that approximates my displacement. That's about how much I moved, from there to there. It's the linear estimate in the limit. Close enough. The force that I'm applying as I move that, some other vector, F, again, approximately constant, because this is an itty-bitty, teeny-tiny little piece. And, so the amount of work moving along that piece, F dot dx. Right? So the actual dw there, dw is F dot dx. And when I add up over the entire curve, whatever that entire curve is, adding up the whole thing, you get this expression right here. Now, not really quite what we were expecting. We're adding up over a curve. Previously, when we've added up over a curve, we got a scalar line integral. We got something that looks like this. Integral, scalar integrand, scalar differential ds. Right? That was the case here for mass, here for x coordinate of the centroid, blah, 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 here for the area of the fence, blah, 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 right? All these examples, not this one though. So this thing here, it's different. We have now, you'll notice, a vector integrand. We have a vector differential. That's weird. Right? And so now it's still a line integral. It's still an integral over a curve, right? So I'm still going to use the term line integral, given that it is an integral over a curve. Again, kind of wish we'd called it curve integral, but anyway. But you see now why it's qualitatively different. So this is not a scalar line integral. These are not scalars. I have to call this, to distinguish it from the importantly different construction we had before, I'm going to call this a vector line integral due to its components being vectors. What do you think? Does that seem all right? Okay. Now, technically that means that this is a totally different kind of a Riemann sum, right? I didn't use Riemann sum notation, but remember all integrals are Riemann sums, right? So, using the luxury and convenience of integral notation, but this is a new kind of a Riemann sum, and thus a new kind of an integral. All right. Okay. So, now, next natural big question, how do you compute these things? And the good news, we actually already have everything that we need to compute them. We've already talked about how if you have a curve, right, you can view that curve as the image by way of a parameterization of an interval on the t-axis. Oh, well, interval on the t-axis. And that you can pull back from the original curve, you can pull back through the parameterization to that interval on the t-axis. And all that you need for the pullback pretty much is to plug in. And what do I need to be able to plug in? Well, everything that I need I already have. What is, in particular, what is dx? Right, this displacement, this position differential. Well, old formulas. We established these formulas long ago, back in section 3.1. Which we did right kind of in the middle of chapter 2, you may recall. So look back, please, to there and remind yourselves of these formulas. And so as such, given those formulas, dx, x prime dt, or if you prefer, tds. And in particular, this the first one is the one that's really the payoff most immediately. If you have a vector line integral, there's a single variable calculus integral that will compute it for you. So, plug and chug. What do you think? All right, now some students do get uncomfortable with the fact that these are equal to each other. These do look pretty qualitatively different. Why are these the same? There's a really nice observation to connect these. I want to show you. And related question a student asked in the earlier lecture today. Hey, where's the stretching factor? Or don't we have to put a stretching factor in there? Seems like we forgot the stretching factor, doesn't it? In fact, it's already in there. It's just hidden. Let me show you where it is. Within x prime dt. Don't forget what x prime is. X prime points in the direction that you're moving. That's what capital T says. Capital T says, what direction are you moving? The magnitude of x prime, of course, is, magnitude of x prime. And then dt. So this thing, x prime dt, is that. And again, you can see it right here. X prime is that thing. Right? So there's your stretching factor. It was just hiding inside of your velocity vector. Okay. But here's the other thing. Same thing here. I claim that the stretching factor is hiding inside of here as well. It's just that this time it's hiding inside of the ds. ds, you'll recall, is speed times dt. Right, so this, it's in there. It's just hiding in one place or the other, depending on how you want to write it. Okay. Is everybody good? Great. Okay. All right, so let's see an example. So the wind's blowing, it's exerting forces. You're having to push to keep from falling over because it's, I don't know, let's say it's a hurricane or something. And you are walking along, let's see here, you're walking counterclockwise along the top half of the unit circle. And just to have a picture to look at, let me draw that real quick. Here's the top half of the unit circle. And notice, though, we are walking counterclockwise. Counterclockwise means we're going this way, like so. Yeah? As we walk along that, we're going to have to, again, push to oppose the force of the wind. And I want to compute the amount of work, it says here. Compute how much work. And so we're going to be computing a vector line integral per the earlier derivation. Does that make sense to everybody? Work is a vector line integral. We're computing work, so we have a vector line integral. Now, the awkward little detail here in this, this is annoying, but it's a unavoidable reality of physics, and that is that when you have a balanced situation, there's opposing forces, right? So, my stylus here, there are two forces acting on this stylus right now. Right, gravity is pulling it down, I'm pushing it up. And so they add up to exactly 0. Of course they add up to 0. This isn't accelerating. The total force is 0. Right? Is everybody with me? Okay. So the point then is that the two forces that are applying to it, the force that I'm applying, the force that gravity is applying, those are negatives of each other. They have to be negatives of each other so that when you add them, you get 0. And thus not accelerating. So when there are forces involved, you got to think through, wait a minute, which of these two force options are we talking about? And notice it says right here, F is what the wind exerts. F is the wind's force. The question asks, though, the amount of work that you exert. And if you want to compute the amount of work that you exert, right, you need to know how much force you are applying. And you are applying a force that is exactly the opposite of what the wind is doing to you. Does that make sense to everybody? So again, F is what the wind is doing. The amount of force that I push, that you push with, is the negative of that. Thus that minus sign. So heads up for that. You always have to be on the lookout for, wait a second, do I need the vector? Is the vector field that was given the correct one, or is it the negative of what I actually need? And you got to think it through in terms of how the question is phrased. Just read it critically. And wait, is this the force that corresponds to the work that I'm computing, or is this the work that I'm opposing, in which case I need the negative? Okay. All right. So again, we are pushing with force negative F, and so we have a line integral, vector line integral of negative F. And now we just get to the computation. How do we compute this thing? Well, we are going counterclockwise, top half of the unit circle. There's a parameterization. Now again, conveniently, counterclockwise. We already know how to parameterize it counterclockwise. The top half only, because we're doing the top half, t only goes from 0 to pi. Right, we're not going all the way around the circle. We're doing just the top half. And then let's see. We know we're going to need to take the derivative. We know we're going to need to take the magnitude of that. Well, the magnitude's clearly 1. Oh, and wait a second. No, we're not even going to need to take the magnitude, right? We're only going to need to know dx. We don't need to know ds. So don't even need to take the magnitude. That's nice. And then, now it's a matter of plugging in. So, was that a... No? Okay. So let's see here. dx is x prime dt. X prime we just computed on the previous page. X prime is that thing. Now you do have to be careful. F is given as y comma negative x. Of course, we're not actually interested in f, we're interested in negative f. There's a temptation to maybe combine those too fast or to do multiple steps in your head all at once, and you can forget minus signs there. I think that's a little risky. I suggest that you rewrite carefully and not combine minus signs, canceling minus signs until you're done. Notice I do need to figure out how to rewrite y. What is y? Well, that comes from the parameterization. Y sine t. Right there in the parameterization. So y is sine t. Everybody happy? Etc. X is cosine t, and then you dot it on out, right? And conveniently, all of this dots to just 1 because of the Pythagorean identity, and super easy integral, and the answer is pi. What do you think? No problem? Everybody's happy? All right. Okay, now here's a criticism of what I've done here. Notice nothing about the statement of the question says anything about how fast I'm moving. Right? The statement of the question just says how you're going to walk along a certain path. It doesn't say you're moving at a particular speed. And yet, I just wrote down a parameterization. A parameterization which prescribes that I'm going to walk along that curve at a very particular speed, the speed in this case being 1. Right, so can you just do that? Can you just, I think I'll decide that my speed will be whatever is convenient for me. Is that legal? Are you allowed to do that? The answer is pretty much yeah, it's not a problem. The point here is that it doesn't matter. If the speed doesn't matter, then yeah, choose whatever speed you like, whatever makes your calculation more convenient. And so this is the upshot here. Line integrals don't depend on the parameterization. So parameterize however you want. No issue. With one little exception, one little micro exception, and that is when you parameterize, you do have to parameterize in the same direction as the orientation, right? So we've already kind of talked about that part of it. In particular, when you're talking about work, if the oriented curve that you're given is this way, right? If that's the orientation that you're given, if your parameterization goes the other way, if you inadvertently parameterize that way, well, you're going to get the wrong answer because you did not follow the oriented curve in question. It's not a question of whether you went too fast or too slow. It's that you're going backwards, right? And that's not the same thing. Does everybody see that issue? I hope that makes sense to everybody. Okay. Now, related question: How bad's it going to be if you parameterize backwards? Are you going to get a completely random answer? Well, actually, no. If you parameterize backwards, all that's going to happen is, on these little pieces, where your dx vector should have been that, you will instead get that. Your dx vector will be off by exactly a minus sign. That'll be the case for every one of these terms, if you will. You will, in each of the terms of this Riemann sum, you will have exactly the negative of what you should have because your dx vectors are pointing exactly backwards. So, in fact, you will get not only a wrong answer, you will get exactly the negative. Right? If you parameterize backwards, you will get exactly the negative of the answer that you should have gotten. And this is a theorem in the book. And there's a related little piece of notation here. If you put a superscript of a minus sign, that's just a convenient way to say, look, I've got this curve C, oriented curve C. I want to talk instead, however, about the curve, same curve, just going backwards. Right? And so the upshot is that when you go backwards along an oriented curve, the value of the line integral becomes the negative of what it should have been. Is everybody happy with that? All right. Okay. All right. So here's another example. This is closely related to the previous example. We are again looking at the top half of the unit circle. And this time, though, we're going to go clockwise. So this way, not the other way. So we're going to need to parameterize same curve, but different oriented curve, different orientation. So we're going to have, well, I'm going to say we're going to have to parameterize it the other way. And this is where things do get a little bit tricky. There's a couple of different tools that I like to think of when I'm trying to parameterize backwards or whatever. So these are not always going to work. These are, as usual, these are tools for your toolbox. Use appropriate tools when they seem to work in your circumstance, if it should happen to work out that way. So here's the first trick, the first tool that I hope will be useful sometimes. This process of going in that direction, I claim, involves thinking about that angle, T. What I've got labeled as T there. Because notice where I'm starting, right? I'm starting, if I'm going clockwise, then I'm starting at this point. This is where T is equal to 0. And then I'm going all the way over to here, this ending point. That's where T is equal to pi. And notice that these values of T always are that angle. So if I'm moving clockwise, this is really my parameter. T, 0 here, pi there. T is this angle, not the usual theta. And that's unfortunate. Because if I want to know the coordinates of the point, if I want to know where I am, right, where is that point, I need to know theta because x and y are the cosine and sine of theta, not this t thing. This t thing just happens to relate to our particular example, but this is not the usual theta. So here's the clever trick. Just observe that the theta that you want happens to be, there's a word, what is it, complementary or something like that. These two angles add up to pi, right? Whatever the geometry word is for that. So this angle T, this angle theta, because they add up to pi, theta is pi minus T. And so now, keeping in mind that what I actually wanted to know is where is this point x comma y. X comma y can be understood in terms of cosine and sine by way of the angle theta. And I have theta. Theta is pi minus T. And so x and y are cosine and sine of pi minus T. Does that work for everybody? That's a neat trick. So one angle here relates to our application. T relates to our application. Pi minus T happens to relate to our, trigonometry experience. And so seeing the connection between the purple angle and the blue angle connects what I have with what I want. Okay. All right. The last little bit here, this is angle addition formulas. I've mentioned this before, so this is a good excuse for me to mention it again. I think everybody should know angle addition formulas for sine and cosine. It's just, they're very useful all over the place, case in point. So make sure you know your angle addition formulas, and applied to these terms here, you get that. Okay. All right, now let me show you a different way to do it. Totally different way to do the same question. Also perfectly fine. It goes like this. I want to find that parameterization. I want to know x and y as functions of t. Here's the thing. that is exactly the reflection over the y-axis of this parameterization, which I already know. This is clever, right? You'd be surprised how often something like this is gonna, kind of fall in your lap. The thing that you want, the parameterization going that way, all of the points as you go along that way are literally exactly reflections over the y-axis of the parameterization you already have. And we know how to do reflections, right? If you want to reflect over the y-axis, right? If you reflect over the y-axis, notice that the y-coordinate stays the same. The x-coordinate gets a minus sign, and that minus sign is exactly right there. And again, we win. We get the exact same parameterization that we got before. Different point of view. Same result. What do you think of that one? Everybody happy? Okay. So, tools for your toolbox again. So now you have a parameterization, and you plug into the usual formula, and yada yada. Let y'all compute that out, and you get negative pi. Good exercise. Make sure you can do this. Right? New parameterization. Vector field on the previous page. Make sure you can fill in these blanks. Answer is negative pi. Okay. All right, now let me show you the third way to do this. So I've showed you two different parameterizations anyway. The third way to do this involves this theorem. This theorem right here that says, if you parameterize backwards, you're just going to get the negative of the otherwise answer. And, that's exactly what I'm doing here. I'm going backwards. I'm going the exact opposite direction along the same curve, same everything else, and so I get the negative of the answer I had previously, and thus negative pi. Same result, right? So in some sense, you don't even have to parameterize anew. You can use your existing parameterization and just realize exactly how wrong it is. It's exactly wrong by a minus sign. We're done. That's really the best solution in this case. Yeah?
Well, it seems like, maybe the vectors should not be the same, but wouldn't, just flipping the bounds also negate it?
There's some, I know, I get where you're coming from. There's some tough aspects of that. So, here's one. If t represents time, right, as a parameter, as you move along a curve, if you say, I'm going to start at t equals pi and end at t equals 0. So you got time moving backwards, and that gives me the creeps, right? I'm not saying that it's not going to give you a wrong answer. I'm going to say that as an argument, I don't know what that means, and we're in dangerous territory, right? The other thing I'll point out is completely unnecessary, right? So rather than observe, hey, I'm going the opposite direction, I'm going to invert my bounds. How about instead just say, hey, I'm going the opposite direction. I'm going to put a minus sign on the answer. Because that's a theorem. Now you're just citing a theorem and there's nothing sketchy about it. So, I'm personally opposed to the switching the bounds thing. I've never understood why that's supposedly advantageous. It's just weird to me. But, And then the other quibbles that I could make, I don't want to go off on a digression, but the way you define an integral, a single variable integral, one could make the case that the way we define single variable integrals is on intervals on the x-axis, or t-axis, whatever, right? Well, what is an interval? If you have an interval, the left bound is always less than the right bound, right? And it's not that you can't define integrals the other way, it's that, it'd be different. That'd be a whole sort of reconsideration of how we defined integrals in the past. So, it's, again, it'll get you to a right answer, but by very sketchy reasoning, so I strongly advise against it. Does that make sense? Yeah. It's a great question. Students always want to know about that, and it's the complaints against it, again, are kind of subtle, if you think about it. But I think it's persuasive to just remind yourself that, am I really going to venture with time travel in my solution to my math problem? Why don't we stay away from time travel? Okay. All right. Okay. Okay. So, next thing we're going to consider is sort of a new interpretation of vector line integrals. Heretofore, vector line integrals have answered one application question for us. It was to compute work. But specifically, to compute work where the understanding was that the vector field represents forces. All right, F represents forces. Let's compute work. Okay, here's the thing. Flashback to chapter 3. What else do we do with vector fields? Well, the other thing we do with vector fields is we use vector fields to represent fluid flows. So, if my vector field no longer represents forces, if the vector field represents fluid flows, well, there's no forces involved. There's a flowing fluid. There's no forces. If there's no forces, there's no work. But so what does the line integral represent? In this context of fluid flows, what is a vector line integral? And the answer is, unfortunately, it is a physical concept that you haven't seen before. So it'd be nice if the answer were something familiar, something that you've already, something you've experienced elsewhere. And it just isn't. So what we're going to have to do here, I'm going to have to describe a new kind of a physical quantity, a new thing that we're going to end up being interested in, and it's going to seem like I'm pulling it out of a hat because you've never seen it before, right? But that said, I'm going to define now a new kind of a physical quantity, and we're going to compute that physical quantity, and the answer is going to be a vector line integral. So, all right, here we go. Okay, so reminder. I like to have this nearby. I didn't want to have to flip back several pages to get back to our diagram and our various alternative representations. So anyway, this is copy paste. That's just a have. So here's the new physical quantity that we're going to talk about. If you have a curve, and if your vector field represents a fluid flow, we can talk about the fluid, the amount of fluid that's, I'm going to say nearby our curve. It's not contained in a tube or anything. I want to look at the sort of the bits of fluid that are for the moment near our curve. And then I want to ask, where are these little pieces of fluid going? So, for example, this little piece of fluid right there that's near our curve, maybe it's going this way. Right? So to some extent then, this little piece of fluid, to some extent, is flowing along the curve. To some extent, this being the velocity, to some extent it's moving kind of perpendicular to the curve. Right? And I want to talk about the extent to which we are flowing along the curve. That's what's going to end up relating to line integrals. This is the new physical quantity that we're going to get interested in, and largely because it's what vector line integrals compute. Okay. All right. So here's the idea then. If I've got a little piece of volume of of fluid, I can compute that how much volume there is in this little piece of the fluid I'm interested in by looking at the cross-sectional area, which does matter. This area is going to matter. Multiply that area, you'll see, times that distance right there, ds. Right, the kind of how long along the curve am I looking at this much area? So area. Oh, whoops. Sorry. ds times area. ds times area gives me volume. And what am I interested in about this piece of volume of fluid? Well, I want to know if it's flowing, along, like, let's say in that direction. What I want to know is the extent to which that flow is along the curve. So I want to know the component of the vector field in the direction that the curve is going, namely in the direction of that unit tangent vector t. And so that's how you compute that component. So no big deal here. All I'm doing is kind of writing down, as applies to this one little piece here, how much fluid do I have, and to what extent is it flowing along the curve. That's what I have over there. And then, of course, altogether, that is just representing one little piece of the fluid. I need to add up along the entire curve, and adding up along the entire curve, right, as I look at the entire curve there, I get an integral, which I can manipulate around a little bit as shown to the right here. So all together, now I've got a big mess. Let me clean this all up. All together, what I have is that, notice, a line integral has showed up in my answer. So I can use the answer to interpret what a line integral is in this context. Right? This line integral represents, when the vector field represents a fluid flow, as we've got here. The line integral represents the quantity that I've computed, namely how much my fluid flows along the curve. Well, not exactly. There is the issue of this area, which you can think of kind of in the denominator over here if you prefer. So I'm going to say per cross-sectional area. In other words, depending on how much around your curve you're interested in, so of course that cross-sectional area is going to matter. Line integral represents the extent of the fluid flowing along the curve. So weird, again, this is a question we've never asked before, but this is what line integrals mean in the context of fluid flows. And it looks like we're out of time. So we will draw a line right there and pick up here on Wednesday, right? Because exam on Monday. See y'all on Monday. Good luck with the studying, and have a great weekend. See you Monday.